In this video, 267, I'm going to talk about the index of refraction. I like to always start this lecture by showing my students a short video. You can just watch the first 30 seconds, and it's really fun, really interesting, because it shows a glass stick that is put into water and also put into oil, and it seems to disappear when it's put into the oil. So I always like to start off with that video. There should be a link that you can take a look at it. So the reason that the stick appears to or seems to disappear in the oil has to do with the properties of the material and the fact that the index of refraction is one of those properties of the material that is going to affect how much the light is going to bend. It turns out that the oil and the glass have the same index of refraction, and so the light is not bending, and so you're not seeing it reflect off of the glass either, and you're not seeing the glass in the oil. So the index of refraction, we use the letter N here, and it's the ratio of the speed of light in the vacuum to the speed of light in the material. We learned before that the speed of light in a vacuum is 3 times 10 to the 8 meters per second. Light slows down when it enters any other material, and we're going to use the letter V to represent the speed of light in any other material besides the vacuum. So to understand this better, you can think about the fact that, well, if the speed is very slow, right, if this v is a very small number compared to the speed of light, then that means that the index of refraction for that material is going to be higher. So you can see how the index of refraction characterizes the speed of light in a material. This variable here is a unitless ratio. There are no units because you are dividing two speeds. I have a table here that shows typical indices of refraction. Vacuum has an index of 1, and that makes sense because if n equals c over v, well, the speed of light in a vacuum is c, so c over c equals 1. It turns out that in air, the index of refraction is also basically 1. We just approximate it and say that it's also equal to 1. And we're going to use the index of refraction of water and glass in different examples, so you can see that the index does get higher for these glass materials and even more dense materials such as diamond. Something to note here is that the index of refraction is always greater or equal to 1 because v is always less than 1. V is the speed in the material, is always less than c, sorry. So looking back at this ratio here, if v is always smaller than c, then this n here is always going to be greater than 1. Let's look at a few your turn questions. The first one says, light is blank in a medium with a higher index of refraction. So this just goes back to looking at this equation here. When you have a higher index, that means that your light is moving slower in that material because C is constant. So light is slower in a medium with a higher index of refraction. Let's look at this next one here. Fill in the blanks. When light refracts into a material with a higher index, the ray bends either toward or away from the normal, but when it refracts into a material with a lower index, the ray bends either toward or away from the normal. So this has to do with the picture that we saw in a previous video that I have copied again right here. We saw this earlier. We said that when the speed is lower, that it's going to bend toward the normal. But when the speed of light is faster, it's going to bend away from the normal. So if we go back at the question here, When it goes into a higher index of refraction, that means it's going to move slower. So we just said that when it moves slower, that means that the ray is going to bend toward the normal. When it's going to a lower index of refraction, it's going to move faster. So that means it's going to move away from the normal. So the answer choice was C for this one. So if we look back at this picture here from earlier, we can say, okay, now that we can characterize these media here with an index of refraction, we can say air has n equal to 1. Glass, we saw in the table that it had approximately an index of 1.5. So you can see that you're going to a higher index, you bend toward the normal. But here you're going from a high index to a low index, and you're bending away from the normal. The last question I have in this section is another one that you should be able to look at this drawing here and figure out which index of refraction is higher. So what I like about this one is that it doesn't show the normal for you, so you have to draw it in yourself. What it shows here are two different media here, and the boundary between the two is this line right here. So the light is going from medium 1 into medium 2. So is it refracting toward or away from the normal? So what you should do is you should draw that normal line, that line that is perpendicular to the surface. This is the normal line here. And I always like to just pretend that this ray of light here is going straight, which it doesn't, but if it were going straight, right, if it were going in a straight line, then you can see that, okay, actually, it went this way, so instead of going straight, it bent away from the normal, because the normal is over here, it bent away from that line. So when the ray bends away from the normal, that means that you're going into a faster material where your light is faster. That means that the index of refraction is lower. So that means that your N2 here is lower than your N1. So the answer was B. In the next section, we're going to actually put some numbers to this and be able to figure out what's the exact angle of refraction and how does it depend on this index of refraction.